So good morning, everyone. It is my great pleasure to welcome George Donati from Wake Forest University, North Carolina, presenting us in our Metrology coffee and learn or lunch and learn seminar about novel calibration strategies in analytical chemistry or spectrochemical analysis. So over the last 2.5, 3 months. Next slide, please. We have been fortunate to have a good half a dozen experts and scientists from all over the world presenting us on various aspects of modern chemical analysis and specifically on issues associated with chemical metrology. And again, today we are extremely fortunate to have George Donati presenting us. I would, next slide please. I would hand over to Jake Carter, the introduction portion. Jake is a student, a PhD student of George, working right now in our labs. Actually, he's not working in our labs. He's sitting at home in his kitchen and writing papers like a machine and getting ready to graduate. So, Jake, please take it away and introduce George. And then, George, the floor is yours, and we are very much looking forward to your seminar. And thank you very much for accepting our invitation.
Thank you, Zoltan.
Thank you, Zoltan. It's a real privilege to introduce George, my supervisor. It's the first time doing this, hopefully not the last, but George received his master's in analytical chemistry from the Federal University of Sao Carlos in Brazil. Then he came to Winston-Salem, North Carolina to get his PhD at Wake Forest University, studying tungsten coil atomic spectrometry, and then participated in 2 postdocs, one back in the group, Jacques Nobrega's group in Brazil, then back at Wake as a teaching scholar postdoc. George is well published, over 80 peer-reviewed papers, 3 book chapters, and he recently just was received the Journal of Analytical Atomic Spectrometry Emerging Lectureship Award for 2020. So I think we've caught him at an interesting point in his career, and I'm excited for the talk. George has been a wonderful mentor, both inside and outside the lab, so I'm excited to be here. So welcome, George, and it's good to see you again, and hopefully I'll see you in person here soon.
Thank you, Jake. Thank you for this kind introduction. And thank you, Zoltan, for inviting us and for having Jake working in our lab. It's hopefully a good collaboration we're starting. Hopefully after all this passes, it will be easier for everybody to work. I'm gonna share my screen here. So let's see. Talk a little bit about calibration today. Okay, so again, thank you for having me. It's a pleasure to be here talking about a little bit of what we do in the lab. And today we're going to talk a little bit about new calibration methods we have developed over the years to try to improve the efficiency of atomic spectrometry in general, but it can be applied to some non-atomic spectrometry applications too. So in this talk, we'll talk a little bit about the traditional calibration methods, the 3 most common ones. Then I'll dive into 3 or 4 of the new calibration methods that we developed: standard dilution analysis, multi-energy calibration, and multi-isotope calibration, and multi-species calibration. So first, why would anybody need to calibrate an instrument to do quantitative measurements? So modern spectrochemical analysis methods, there are too many factors involved in generating the analytical signal. So if you look at this equation, you can see how the factors that could, and here are what they mean. So you have atomic concentration, solution flow rate, and so forth. So it's very hard to control all this and reproduce in time. So if you run a calibration curve now, you come back tomorrow, the signal is not going to be exactly the same because of all those factors that will change from now to the next time. In fact, it's advisable to rerun a calibration curve every 20, 25 samples, depending on how long it takes each measurement. But every time to time is good to do recalibration to make sure your signal matches the conditions of that moment in time. So usually what people do then to overcome those variations due to the instrumentation, this is an example, an equation for atomic emission, but it could be any other kind of measurement using instrumentation, modern instrumentation. So usually what people do is to have instrument response and everything else becomes a proportionality constant and the concentration of the analyte. So then basically run several solutions of known concentration, calibration standards, to determine a mathematical model that will tell you the relationship between instrument response and analytical concentration. So with that, you keep this set of parameters relative to that concentration of the standards. So the traditional calibration methods, the way people mostly do, those three are the most common ones: external standard calibration, internal standards, and standard deviations. There are others, but they're more specific. Those are more general. So external standard calibration is the simplest and most common use. So it's the normal calibration curve where you run several standards and you compare it to a set of samples later. So it assumes, and this is the main limitation, it assumes negligible matrix effects. And there is no correction to those signal biases caused by the matrix or any other factor in the measurement. And in terms of atomic spectrometry, it can be used in anything: flame atomic absorption, flame atomic emission, graphite furnace atomic absorption, ICP-MS, ICP-OIS, LIBS, microwave induced plasma optical emission. So it's the most common one. But although a very effective for most applications, it can be a little less accurate when you have matrix effects. Then to overcome that kind of limitation, you can use an internal standard. Most of you probably already used an internal standard where basically you choose a species that has behavior similar to the analyte. Then whatever happens with the analyte hopefully will happen to the internal standard. Then if you take the ratio, that change in signal will be neutralized. So then you use the ratio of analyte to internal standard as the y-axis in your calibration curve. It can correct for instrumental drift and for less severe matrix effects. It also can be used in most measurements as long as you can measure both analyte and internal standard at the same time or very quickly, one after another. Then the best one of the traditional ones when you have matrix effects is standard deviations. So because, for example, in external standard calibration, you assume no matrix effects, you are running a clean matrix as a standard calibration curve, and the sample sometimes doesn't have that simple matrix. So when you compare the standards with the sample, there is no good comparison. So in standard deviations, you basically use the sample as the matrix and or the basis to prepare the calibration solution. So you add standards to increasing concentration to the sample and run that, and then you determine the concentration of the analyte in the sample. So you correct matrix effects that way. I'm not talking about correcting known matrix effects. Spectrometric spectral interferences, for example, are not corrected this way, but this is more on an instrumentation level. And what I'm talking about, matrix effects, more general. So talking about this, we have if we talk about external standard calibration, it's not going to correct matrix effects. Internal standards, the main limitation is to find an internal standard that matches the analyte. So it's not easy to reproduce the behavior of the analyte. And then the standard additions is a very time-consuming, labor-intensive method because you have to prepare a calibration curve for each sample. So we have several solutions for each sample. So the new methods we try to develop, one of them being standard dilution analysis, is to try and overcome some of those limitations the traditional methods have. So I'm going to talk a little bit about standard dilution analysis, which is based on two calibration solutions. So the first solution you're going to prepare with half sample and half standards. This is a standard solution which has analytes and has one internal standard. Then you have another calibration solution where you have half sample and half blank, whatever the blank is. Usually nitric acid 1% is what you usually use. And when you do the calibration, you see in a minute, you mix those two solutions and you measure the signal as those two solutions are mixing. So note that the amount of sample in the solutions is exactly the same. So even when you mix those, there is no change in the matrix. So because it never changed, there is no matrix effects expected in that case. So it combines standard additions and internal standard. You have an internal standard here in the first solution, and you are having the sample as a matrix all the time without changing. So it combines those two traditional methods. But it only uses two solutions per sample. So in that sense, it's quicker and easier than standard additions. So in general, it provides improvements on accuracy compared to external calibration and external standard calibration and internal standards. And sample throughput is going to improve sample throughput when compared to standard additions because you have less samples to prepare and run. So how does it work? So first, we are going to introduce the sample into the instrumentation. Here's an example of vinegar analysis in ICP-OES. So we're going to introduce solution one, again, half sample, half standards. So as you introduce S1 here, so you have a blank going into the system, you introduce the sample, the signals go up. So you have several analytes here, and the internal standard in this case is yttrium, all in that first solution. Then as that solution is running through the instrument, you have a plateau of signal, the signal stabilizes, then you add the second solution. When you add the second solution, the signal goes down, right? So it goes down because you are adding the same matrix, but you have half blank in there. So the standards are being diluted, not the sample, because the sample stays the same, but the standards are being diluted. That's why the name standard dilution analysis. So what happens then in that region where we call the SDA region, standard dilution analysis region, you have several different signals and concentrations attached to them. So the idea here, you have many points of a calibration curve. The same way as you would prepare a calibration curve with increasing concentrations, in this phase of the measurement, you have several concentrations with time that can be used for calibration. The math behind it looks like this. So let's say you have the signal from the analyte and the signal from the internal standard. We take the ratio of those two. So the signal from the analyte is basically a sensitivity of the analyte times the concentration of the analyte. And the same thing for the internal standard. Now, the concentration of the analyte, because of the way the solutions work, you have signal coming from the sample itself and coming from the standard, because the way we prepare the solution with half sample, half standard, and the other one half sample too. So the concentrations here come from both. Then you can separate this, looking like this, and basically you can plot the ratio on the y-axis against the concentration of the internal standard, or the inverse of the concentration of the internal standard on the x-axis. And again, if we go back here, this concentration is going to change, you assume the maximum here is the concentration you know you add of the internal standard. As you go down, you consider that linear, and it's just a proportion. So that's the way you know the concentration of the internal standard. So when you plot that, and the slope is going to be this whole thing here. So the slope is this, and the intercept is this of that calibration plot, which is that. So then we can rearrange this and isolate the concentration of the sample, the analyte in the sample, and it becomes this equation. This is what we're going to use. We just need the slope and the intercept of that plot, and those two concentrations which you already know and are constant because we prepared the calibration solution and we know how much we add in the beginning. So when you plot, excuse me, it looks like this. So you have the ratio y-axis, 1 over the concentration of the internal standard on the x-axis, and you can see it's very linear. Here, several examples of calcium determination in apple juice, nitric acid, or cola soft drink and ICP-OS. So you can see it's very linear there. Then applying this, again, we just need the slope and the intercept and the two concentrations, standard and internal standard. So when we apply that to, I'm just going to show a few results of this. This is two reference materials, or standard materials, different elements, and you can see the recoveries are, if not similar, sometimes better than the traditional methods, the standard calibration, standardizations. Usually does a good job in terms of accuracy. And the main goal here is to improve accuracy and sample throughput. Here's another example, some kind of nasty samples. There is no digestion in this case, so just dilute and shoot. We spike with 2 ppm and ICP-OS, and the recoveries were quite good for those elements. Here's a more challenging application. The microwave-induced plasma has lower plasma temperature, so it is more prone to matrix effects. And in here we have several beverages, coffee, whiskey, beer, just diluting those and measuring directly on the microwave-induced plasma by optical emission. So it's a very bad situation in terms of matrix effects because of the low temperature of the plasma and because we're not digesting anything. And you can see the calibration is very linear again. And here's the profile of the signal. Before we add the second solution around here, the signal goes down and we use those points there. You can note that we have less points now when comparing to the ICP-OS because the microwave plasma is a sequential measurement. So you have less, it takes a time from going to one analyte to the next. So in time, the dilution is happening. If it takes time to go from one analyte to the next, you lose some time in that, so you have less points. But that didn't matter. We got some good recoveries for many nasty samples with an average of recovery, again, similar, if not better than the other traditional methods in general for all the analytes evaluated here. We also applied that to ICP-MS. The same problem we had with the microwave plasma, we have the ICP-MS. Is not a simultaneous measurement as in ICP-OS. You have a little time to go from one element to another. So you have less points in the measurement. It still is a quick measurement. It's enough to have enough points to do the measurement. And here's some measurements in concentrated acid, several elements, and the comparison with the other traditional methods, usually good accuracies. We also applied that to Raman spectroscopy. So this is not atomic. This is an example of non-atomic spectrometry, but you can see the same drop in signal. So here's the plateau. You add the second solution, it goes down, and you use the points to do the calibration. In this example, we're determining ethanol and using in gasoline and use the acetone as an internal standard. Here's some of the results. It was used a liquid extraction and flow analysis to do everything online. And here's the comparison of the SDA with the other methods. This is the official method, the Brazilian official method of measuring ethanol in gasoline. In Brazil, it's very common to have 20%, 25% ethanol in gasoline, which makes it sometimes cheaper depending on the time of the year, and also less, it produces less pollution. So they have an official method to measure ethanol in gasoline. So the standard dilution analysis method was used for ICP-OS, ICP-MS, flame atomic emission, microorganism plasma, even UV-vis for some dye measurement in food dyes. So it's a very broad application method for calibration. Precision and accuracy and LODs, I didn't show any LODs here, but they're usually comparable to the traditional methods. And the main goal of the method is improving accuracy. Sensitivity is not changed much by using this application. So it also helps with improvement in sample throughput when compared to standard additions, because you don't need to prepare as many samples and run as many samples. Well, there are some limitations to the method. First of them, two main limitations, I'd say. One is data processing. You need to choose that SDA region well. If you don't choose it correctly, the accuracy is not going to be good. You want to make sure it's in the time where the two solutions are mixing. So that makes a little bit of a difference. And it's challenging because you need to do that by hand, which is a lot of work because you need to find where each sample run and all that. Or you can use an algorithm, which is not very easy either. Another limitation is automation. You need somebody there to pour one solution on top of the other every time. And this needs to be done slowly so the mixing happens well. So this is not easy to automate without changing whatever is already in the lab, like an auto sampler, for example. So to try and overcome those limitations, we came up with an automated method using two internal standards. So the new SDA used two internal standard samples. With that, I'm going to show the graphs and the math in a minute. You don't need to choose that SDA region anymore. So you don't need to go back and choose the SDA region. You can use the whole thing. So that makes data processing much easier. And for mixing and automation, we just use a syringe, a plastic syringe, where you have the sample 1 and sample 2 mixing inside here. And this helps with automation. You just use the auto sampler of an ICP to run the samples. So you don't need anybody there mixing by hand. Here's the general idea. So you introduce the sample coming from the auto sampler. The sample gets into the chamber. The tubing going out the waste is a little bit smaller than the one from the entrance here. So sample will accumulate inside of the syringe, and then it goes to the ICP-OS. Then you will change the auto sampler to the second solution. The second solution comes in and start mixing with the first solution, and then that mix goes to the ICP-OS. So in this example, you have zinc and yttrium. So if you look at the graph, the first solution will have half sample, half standard, and the standard will have yttrium, in this example, the first internal standard as the internal standard in that case, and zinc is the analyte. So you can see the signal after reaching the plasma is going to be stable. And for the second internal standard will be applied to the second solution. So the second solution has half sample, half blank, but that blank has scandium, a second internal standard. See that the only difference before was we didn't have that second internal standard. So then that is going to be mixing, and the equation I'm going to show in a minute is basically like this. You need the intercept and the slope, just like before. You need the analyte concentration, just like before. And you need the intercept of a second graph I will show in a minute. As soon as you add that second solution, the graph is going to look like this. So the analyte and the first internal standard in the first solution will go down in signal. And of course, because the blank has the scandium, that signal goes up. Here's a little video so you can have an idea of how that looks like in real life. So you can see there the sample 1 is getting into the syringe, and that syringe is going to fill up because of the different in tubing size there, and it goes to waste, but it's going to fill it up. And as it fills it up, the sample will go out through here and go into the ICP. So there's a little fast forward there, and the sample will start going through the ICP. As you go through the ICP, that first part of the graph is taking place. Then the auto sampler will move to the second solution, and that second solution comes in, start mixing, and it goes to the ICP, in this case an ICP OES. Then after that is done, all the measurement is done, you just move to a rinse solution to make sure you clean the tubing. Again, this is all automatic, it's all set up in the auto sampler software. You don't need to, you just need to put the solutions there. Then finally, you need to clean up, get rid of that solution so it moves to an empty tube to introduce air and clean up the whole syringe. Once that happens, you can move again to the next sample and start the sequence again. So that is general what happens with the SDA in terms of automatic setup. Again, we need the slope here and the intercept of the one of the graphs, and then the second intercept of the second graph. Let me show the graphs is easier. So I have the first graph with analyte on the y-axis, internal standard on the x-axis, and we use both the slope and the intercept for the calculations. And then we use the intercept of this graph, which is collected at the same time. You just need to use the data there. So we have the first internal standard against the second internal standard, and you just need the intercept there, which gives you basically the maximum of the first internal standard so you can do the calculations. So we apply that first doing the manual SDA with two internal standards just to check whether the two internal standards method works. And you can see the recoveries are very similar to the standard additions. We here manual SDA against the external standard calibration, internal standard additions for 3 different elements, and the recoveries are quite good. And then we compare the manual SDA with automatic. Now, in both cases, we have 2 internal standards, and there is not much of a difference. So we're happy to see that it's possible to do manual or automatic, and there is no change in the accuracy of the measurements. And again, we apply to some nasty solutions. You can see here, for example, calcium is a very nasty concomitant that can mess up the measurement, and some others here that just dilute and should no digestion, and the recoveries were quite good. So then a final method that we try to improve on that one. The main trouble with the previous method is it takes a little while. It gets about 6 minutes per sample, so it's a little longer. So we try to do it even better or more automatic. So we use a pinch valve here, and the idea is that pinch valve does the mixing of standard and blank. So the sample comes from the auto sampler and goes to the ICP. And then standard and blank, when the switch valve is on this position, the blank is open, and you move this every time, every 60 seconds. So when you move this, you go from total blank to total standards in every cycle. And then this mix with the sample there. So the sample will still have the same amount of sample, but increasing concentrations of standard. It could be decreasing too, depending on the cycle. And once you do that, you have the same effect as you saw before for this range. And here is how it looks like. Every cycle of 60, and here's the total cycle going up and down. But you can see signal of the analytes here going up first with the first internal standard, and the signal from the blank with the, in fact, not the blank, but the second internal standard going down, and it goes up. And this is the cycle through the measurement. And with that, you can have many, many points to do the calibration curve. Here's an example of the graph, of the first graph with analyte and first internal standards. And you can see many, many points can be used. No need to choose that standard SDA region. And another interesting component of this, you can see the slope doesn't change much, but for different samples, you have different intercepts. So the intercept can tell you how bad of a matrix effect you're going to have. For example, tap water here, I'm sorry, deionized water. Up here, you have a certain intercept. And then when you have calcium 1%, which is one of the worst matrix effects, you have a much different intercept. That doesn't change the measurement because we use the second internal standard. Doesn't matter where it is. The only thing is visually, you can see how bad that matrix effect is before you do the whole calculation. So we applied that method to several samples too. And again, good recoveries. Here's an average of 8 elements. This is the recovery for all of them, many points in the measurement. Or looking the other way, you have all the analytes, but this is an average of 9 different matrices. And again, the recoveries are quite good. So the SDA basically will make things easier and more accurate than the traditional methods. That's the main idea. So this is the SDA. I'm going to talk a little bit about the multi-energy calibration methods now. So it's a little different setup where you don't need to mix the solutions. So it makes automation a little easier in terms that you don't need to add anything else to the system. So the multi-energy calibration is most adequate for multi-signal analysis method. So you need to be able to measure several signals from the analyte. So atomic absorption, for example, using a flame, unless you have more lamps, it wouldn't work. You need to measure several signals at the same time. It's based on the same setup with 2 solutions per sample, and the way to prepare the solution is very similar. It also improves accuracy compared to EC and IS, and improves sample throughput when compared to standard editions. So the whole idea is when you measure an instrument response, a signal, here's an example for atomic emission. Again, you have several factors. You have analyte concentration, and you have among those transition energy. And excuse me, in a traditional method, what you do, you keep everything constant, including the energy transition of the same wavelength, and you vary the concentration of the analyte. Then you prepare several standard calibration solutions so you can vary that concentration, and you use a linear function of instrument response against concentration. That's the traditional calibration. For the multi-energy calibration, we switch this a little bit. So we keep concentration constant, and we vary the energy transition. So we measure the analyte signal in several wavelengths at the same time. That way, we can only use 2 calibration solutions because the concentration of the standard is constant. And we do matrix matching at the same time because we use something similar to what we did for SDA. Here's the whole idea. 50% sample in the first solution, 50% standard with only analyte. See that in this case, we don't need the internal standard. And the second solution, the same as we did for SDA, half sample, half blank. If we look at the signal at a certain wavelength, the instrument response is based on a proportionality constant times the concentration of the analyte, which comes from the standard and the sample. And in this solution, it comes only from the sample. Then you can, because this proportionality constant is the sensitivity of that wavelength, you can equalize those 2 equations, and it looks like this. Then what we do, if we plot, for example, this in the y-axis, so the intensity coming from the sample, and the intensity coming from the first solution, sample plus standard, if we plot those two, you can see you get a very linear curve, and each of these points represents a different wavelength. So you see you have intensity for each of the solutions in one wavelength, another wavelength, and so forth. In this case, in this example, we have 10 emission lines of chromium for this measurement. Then, if you do that way, this whole thing here is the slope. So the slope looks like this. We can rearrange that and isolate the concentration of the analyte in the sample, which is what you're interested in. So the equation to solve it is very simple. We just need a slope now of that graph and the concentration of analyte, which we know because we prepare that solution. This is known and constant. So in this example, let's say the concentration, and just to put some numbers on it, concentration of the standard is 1 ppm. When you apply that slope to this equation and 1 ppm, you get 0.49 milligrams per liter. In this example, it was expected 0.5 milligrams per liter, so 98% recovery. Again, the way the setup works, there is the same amount of sample in both solutions in every change, so no matrix effects expected, just like SDA. Another thing about this, you don't need to mix those two solutions. So the auto sampler goes to the first solution, measure it several wavelengths, go to the second solution, measure several wavelengths, and then you do the calibration. The one-to-one sample standard mix, because we use half-half, is just for simplicity. It doesn't need to be like that. It can be 40-60, 30-70, 60-40. It depends on what you want to do. So you can use more sample, like here, for example, to increase sensitivity, or you can use less sample to increase or to minimize even more the matrix effect. So the only thing you need to do is to include the volumes of standard and sample into the calculation. And note that when those two are the same, this goes back to the equation we had before. So you can work with any proportion in that case. We just use half-half because it's more convenient. So we apply this to, again, several samples with no much dilution. This one, there was a digestion, but all the rest, no digestion, just dilute and shoot. And you can see the recoveries are quite good compared to the traditional methods, usually at least similar, sometimes better than the traditional methods. In these examples we use for microwave plasma, ICP-OAS, graphite furnace, in this case a high resolution continuous source, flame atomic absorption spectrometry, where you can measure several peaks from the same analyte, several absorbance from the same analyte, the same window. And you can have several emission lines. Here's the LODs. In one thing I need to mention, the LODs are usually a little higher than the traditional methods for multi-energy calibration, because you are using either some emission line that is not very sensitive, and that messes up a little bit the sensitivity. But again, the method is not too different in terms of limit of detection to the traditional method, a little worse. And the whole goal here is to improve accuracy rather than improving the LOD. So we apply this to some nasty solutions on top of those that I was talking about. These fertilizers, for example, very nasty measurement. You can see by the recoveries of external standard calibration and standard additions that are usually not very good. And for MAC was pretty good in the measurement. This is microwave plasma, which is also very prone to interferences. Another very good application of MAC is with LIBS, because LIBS has the problem with calibration being difficult. You are working with solid samples. You have very severe matrix effects, but it also produces several lines at the same time. Every shot of the laser will produce many emission lines. So this is a great marriage of MAC with another technique. and it has been applied to mineral supplements for cattle, ores, sediment, brick clay, liquid displays, LCDs, dietary supplements, and many other things. And with very good recoveries and good accuracy, very easy to apply. This is one of the best applications of MAC because of the difficulty of using libs. So in general, it's being applied to all these techniques, and you can see very nasty samples, just usually dilute and shoot. Most of them, maybe one or two here are needed to be digested, like the cough syrup, but all the rest is just dilute and shoot or direct solid analysis using libs. So very robust application of multi-energy calibration. Is very easy to apply because you don't need to change anything in the setup of your system, and it works very well. Now, just to finalize here, I'm going to talk about two calibration methods that are kind of derived from the MAC method. In multi-energy calibration, we just look at different wavelengths, and in here we're going to look at different isotopes, and ICP-MS are different species produced in the ICP-MS. So the multi-isotope calibration is the same principle, same concept of MAC applied to mass spectrometry. Same, you can see the same equation is used. Instead of using multiple wavelengths, we use multiple isotopes. Because of that, it's a little more restrictive because you don't have as many wavelengths as you have isotopes. So you need at least two sources of signal. In practice, you need at least three isotopes. We apply that, and the equation again is the same, just need signal for different isotopes. You can see here different isotopes of cadmium, of barium, all of those, and we apply it to different reference materials with very good accuracies for all of them when we apply the multi-isotope calibration. Here's the comparison between the MICal, it's called multi-isotope calibration, against the other methods. And in general, the recoveries are comparable, if not better, than the traditional methods. Then another application that is extracted or derivated from MAC is the multi-species calibration. In here, we are thinking about, well, what happens if we want to use isotopes, but we only have one isotope? So then what we can do is to use a tandem mass spectrometry and then produce some species in the reaction cell and use those species as sources of signal for our calibration. So in this example in there, so you have a quadrupole, then you have a reaction cell and another quadrupole. So in the reaction cell, you produce many species of your analyte. It could be an oxide, double oxide, or an ammonia cluster to produce those species. Here's an example for cobalt applied to tomato leaves, reference material of tomato leaves. So we use all those, each of those points correspond to one of those species, cobalt by itself, with ammonia, with two ammonias, and so forth. And then in this example, just to show some numbers, here's a replicate of the sample digestion. It was used this mass, it was diluted to 25 ml. Then we use this standard concentration, applying that equation again, where we have concentration of the standard and using the slope of the calibration curve. So that gave us, using that slope and this concentration, gave us this concentration in the sample, which is very close to the reference value of 0.57. So you can see very accurate measurement. And here is the application to bovine liver and tomato leaves for 3 monoisotopic elements, where we use oxides and ammonia cluster species to do the calibration. LODs, usually, as I said, a little higher than the normal calibration, but still 70 ppt, 30 ppt is not bad at all to measure those elements. And RSTs can be a little high sometimes because of the variation on the reaction cell, but for a quadrupole ICP-MS is not that bad. Here's the application then to some real samples there: white rice, brown rice, bovine liver, pork liver, some difficult samples here, and the results were in general comparable to what we found in the literature. Of course, this is not, there's no spike, it's just the concentration in the sample itself. So in summary, just so we wrap this up, SDA is a combination of internal standard and standard additions. It's done in flow, can improve accuracy and sample throughput. We can do automation and add a second internal standard to expand its applicability. And it's most efficient if you can do simultaneous, but fast sequential also works. The other three methods, you need to measure several signals at the same time. It is also matrix matching. You only need two standard solutions, just like SDA per sample. So you can improve accuracy and sample throughput compared to SA, for example. Another interesting thing, you can look at the calibration curve. If any point is off the calibration curve, that is an indication of a spectral interference, which you couldn't do with a traditional method. So any point off the curve will indicate a spectral interference, not matrix interference. So it can be used that way. The main limitation would be you need to be careful when you prepare the calibration standard. Same thing for SA, because if you mess up that one, you mess up the whole measurement. So hopefully that standard you do with care and the conservation is correct. Then this is kind of the summary of the summary. All of them are compared to standard additions. It can significantly minimize rotational interferences, matrix effects, and you can do efficient analysis. Just a final acknowledgement to thanks again, Zoltan and Kelly to inviting me and for this opportunity to be here talking about calibration methods, as the NSF for the grant for acquiring our ICP-MS, Department of Chemistry, and the grad school for supporting our work, and our collaborators in the US and Brazil, and our students will help us collect some of this data. Thank you, everyone.
Thank you very much, George. Exciting presentation. I enjoyed very much.
Thank you.
I would kick off the questions, if I might, and then we would do questions from the Zoom space, and then Kelly would read us the questions from the YouTube live feed. So I am just wondering that with the multi-energy approaches, whichever permutation you used, isn't this very heavily dependent on the concept of having uninterfered signals in each of the channels what you are using on the calibration? And how realistic is that in a typical ICP-OES or ICP-MS measurement to have uninterfered isotope or spectral bandwidths, or if not uninterfered, interfered the same manner?
Right. So in general, for what we've been applying, we chose the ones that are less interfered, and you can get usually 10. Thinking about emission, you can have about 10, 15 signals that are not interfered on spectrally. One nice thing of the graph is if you see any point off the curve, that one might be one that is interfered by some other analyte. That line or that isotope might be having spectral interference. So in general, you get away well with spectral interferences in this case. We have up to 10 lines sometimes less, times 5. But the nice thing is you can see that when you plot the curve, you can see the points off the curve as the interfering species there that will mess up your measurement.
So I would open the floor for question here on the Zoom call. So please just unmute yourself and ask your question.
Hi, maybe this is Yoris May. Maybe I can have a question. You had a very, very nice talk, and I must say that we have applied successfully your multi-energy calibration at NRC already in the past. So we just haven't been brave enough to publish on it, but it's we've been able to make it work for us. But I wanted to ask you a question. Is that many of your techniques that you are employing are hardwired on the linear assumption of linear response, and how much you have looked into that and the perturbations or deviations, how much of an effect that has?
We did some study to see, to kind of put some boundaries where you can apply. This is especially for MAC and the other multi-signal techniques. So we try to put some boundaries, what we should use between this and this concentration and so forth. So when you do that, basically, there's a recent review that we talk about calibration in general, where we talk about that kind of boundaries. Basically, you can run your sample and run a standard, and by the ratio of those signals, you can tell if you were in a region where you can apply the method. The idea is you shouldn't have a slope that is too much higher than 0.9 or too much lower than 0.1. In that case, if you have that outside those boundaries, it means you have too much signal from the standard or too much signal from the sample comparatively. So it's better to work in that range. And this takes care in general of the linearity. If you are working that region in general, you are working in a linear range. Another caveat of that is it requires a little bit of experience with the instrument too. I mean, you wouldn't run a 5 ppm solution in ICP-MS, right? So you need to know where you should work. You know, it should be linear. So then it's a combination of things, a little bit of experience, and that test that you would do that test even for standard calibration. You want to have an idea where the signal is so you can prepare the calibration curve. You can do that with MAC2, where you run the sample in the standard, take the ratio of those signals, and based on that, you can estimate where you are, whether you are in the real good part of the measurement. And in that case, you can dilute the sample or prepare a more concentrated standard.
Thank you.
And I'm glad you guys are using it. It's good to see it's working for other people too.
So do you need the more sample, like for this part, especially that standard analysis, like the first method? You mean you have more samples prepared? Yeah, do you know for one run, basically you need what, 3 milliliter, right?
The amount of sample for SDA.
Yeah.
For SDA, you can work with, it depends on how much your instrument uses of sample, but I would say 5 ml is enough, 3 ml is enough. You just need to prepare half and half and mix them. So for SDA is more demanding in terms of volume because you are doing that mix and dilution. For MAC is not a big deal. As much as your instrument needs is as much you need of sample.
Yeah. When we do the multi-energy analysis, so it's still we need to find out the less interference, less spectral interference lines, right?
That's correct. That's correct. Yeah. You would choose the ones that are least interfered. Yeah. And then again, when you plot it, you should see if there's anything that is being interfered, is going to show off outside of the calibration curve.
Yes, yes, yes. So it's good that we can rule out which lines are interfere also.
That's true. That's true.
George, have you tried any of these calibration approaches in a transient environment? Let's say in a GC MS or GC, FID or LCUV type environment?
I did some tests preliminary for the GCMS. The trouble with, I don't know, I did that very quickly and then I went to atomic, which is I use the most. But the trouble I got was the way I thought to do it is to use fragments of the molecule as the sources of signal, right? The trouble is the fragments are not always the same every time. Some are, there are a few there are, but not all of them will. And also to work with the data processing of that is complicated because of where they show up, right? So that was the main trouble. And then because it took off in the atomic and it is my specialty, I never came back. But I would say I got some preliminary data that are okay, but need some improvement for data processing and repetibility when you apply it.
Yeah, because it's also in an LCMS type setting, and with in-source fragmentation, you can have a multi-channel type, calibration environment created. So basically to mimic your multi-energy approach. Yeah.
That'll be interesting. With you can produce as many as you want and make them repeatable. You can repeat that every time. That would be great.
Maybe we can take this conversation offline. I mean, there's some
it would be nice.
opportunities there.
Sure.
So any more questions from the floor here, from the Zoom call? Going once?
And so,
yes, Indu?
Yeah, so basically traditional method, we collect the number of counts, right? So in this we have to, like STA method, we have to do like a time scan. Is that right?
It's not quite, it could be a time scan, but you mean for SDA?
Yes.
For SDA, yes. But the trouble is sometimes that is a little tricky. What we did was to trick the instrument and collect several replicates. So it does several replicates there, and then you have that signal. But it could be in time scan too.
Okay. Yeah, that's all right.
Thank you.
So Kelly, any questions from our YouTube channel?
There's one question up here on the YouTube live chat relating to the standard dilution analysis. It is, how does any possible time delay or difference between the two traces in the dilution region affect the calibration?
Yeah, that is a trouble for especially microwave-induced plasma, which is not simultaneous. Is you have a little bit of a delay between the traces. So one way we deal with that is to take a moving average of the signal. So that helps a little bit with that delay. And in the end, another thing you need to do, you can't have too many elements measured at the same time for microwave-induced plasma. Otherwise, it's not enough time to catch the dilution. If it takes too long to go to the last analyte and go back to the first, then you don't catch all the dilution. So there is a limitation when you apply to sequential instruments on the number of elements you are measuring. For ICP-MS though, the one with the switch valve, we did like 20 elements and it worked very well for ICP-MS. So because ICP-MS is very quick compared to the microwave-induced plasma.
Okay, so I would like to thank Professor Donati for coming to Ottawa, even if it's only virtually this time, and delivering us this very exciting presentations. I think we heard enough ideas for many potential future student exchanges and projects. So thank you very much, George, for delivering this very exciting lecture, and hope to see you soon in a non-remote or non-online environment.
Thank you, Zoltan. It's a pleasure, and thanks again for the opportunity. And it's great to discuss these ideas here and hopefully in person soon.
Okay, thank you very much.
Thank you.
Goodbye.
Bye. Take care.